This is section 15.1. We're going to be talking about graphs, paths, and circuits. Chapter 15 is graph theory, which is not the same thing as graphing. You would not have studied this in any class that you've taken so far. We're going to talk some vocabulary first. Vertices, finite set of points. The singular of vertices is vertex. Line segments or curves called edges, and all graphs have vertices and edges. Vertices and edges. The vertices are the points and the edges are the line segments or curves. They do not have to be straight. Notice this point right here, which does not have a labeled point. It does not have a labeled point. That is not a vertex. Unless they actually label it, it's not going to be a vertex. When you have an edge that goes from a point back to the same point, we call that a loop. An edge that starts and ends at the same vertex is called a loop. We talked about that. A graph consists of vertices and edges that start and end at vertices. Explain why the figures below show equivalent graphs. Well, if you look at the graph on the left, we have a vertex A, B, C, and D. You look at the graph on the right, we have again A, B, C, and D. So they have the same number of vertices and the exact same labeled vertices. And next, if you look at the edges, the graph on the left has an edge going from A to B. The graph on the right has an edge going from A to B. On the left, we have an edge going from B to C. And on the right, B to C. On the left, C to D. And on the right, C to D. So these graphs are equivalent. They're basically, we can consider them the same graph, even though they look completely different. They have the same number of vertices, the same labeled vertices, and the same edges going to the same points. In the early 1700s, the city of Königsberg, Germany, was located on both banks and two islands of the Pregel River. The figure below shows that the town sections were connected by 7 bridges. This is called the 7 bridges of Königsberg problem, by the way. It's a very famous problem. It's actually the problem that originated this study called graph theory. Draw a graph that models the layout of Königsberg. Use vertices to represent the land masses and edges to represent the bridges. Okay, so we have a land mass called the right bank. We have a land mass called island right here. We have another island right here. And we have the left bank. Now we need the 7 bridges. So we have 2 bridges going from the right bank to this first island. 2 bridges. We have 1 bridge going from the right bank to this island. We have 1 bridge going between the 2 islands. We've got 2 bridges going from the left bank. This is our left bank, so 2 bridges. 1 and another one. And we have 1 bridge going from the left bank to the other island. So this would be 1 graph that represents the layout of Königsberg. The map of New England states are given below. Draw a graph that models which New England states share a common border. Use vertices to represent the states, edges to represent the common borders. So we have Maine, and we have New Hampshire. And it doesn't matter where you put the vertices, I just put them as the same layout so I can remember which one's which. We've got Massachusetts, Connecticut, and Rhode Island. Now we're going to look at Maine, and we need the common border. So does Maine share a border with any state? Well, yes it does. It shares a border with New Hampshire. So we need an edge going from Maine to New Hampshire. And that's it. Maine is only bordered by one state. Now we're going to look at New Hampshire. New Hampshire is bordered by Maine, but we already took care of that one. And Vermont. So we need an edge going to Vermont and Massachusetts. Now let's look at Vermont. Vermont is bordered by New Hampshire, but we already did that one, and by Massachusetts, so we need an edge going to Massachusetts. We look at Massachusetts, it's bordered by Connecticut and Rhode Island. We got Rhode Island here, and then Connecticut and Rhode Island share a border. So this would represent the New England states. The degree of a vertex. For some reason, students find this difficult. I'm not sure why, but pay attention when I talk about the degree. The degree is not like temperature. It's not like degrees in a circle. It's not like degree angle. The degree of a vertex is the number of edges at that vertex. A vertex with an even number of edges is called an even vertex. Odd number of edges is called an odd vertex. Two vertices are said to be adjacent vertices if there is at least one, doesn't matter how many, could be 15 edges connecting them. Let's take a look at the graph. Look at point or vertex D has degree 2 because I have this edge coming into it and I have this edge coming into it. B has degree 3 because I have this edge, and this one. Look at E. I have this edge coming in, so that's 1. I have this edge coming in, that's 2. When you have a loop, you have the edge coming in from this direction and you have an edge coming in from this direction. With a loop, it counts double. You count it twice. So the degree of E is 4. Be careful with loops. List the pairs of adjacent vertices. They just have to have a connecting edge. E is adjacent to E because they have a connecting edge. The loop means it connects to itself. E is connected to A. A is connected to C, to D, and to B. and B is connected to C. They are, when I say connected, I'm saying they're adjacent. A path is a sequence of adjacent vertices and the edges connecting them. For this graph, we used arrows to represent a particular path. So if I get the file back, so let's suppose I want to start at vertex A, and then go to B. Well, notice the arrows have you going to B. These arrows, they aren't edges. They're just trying to tell you the direction of the path. So this path starts at A, and then it goes to B, then it goes to D, and then it goes to E. So this path shown by the arrows would be described by A, B, D, E. A circuit is a path, but it's a specific type of path. It begins and ends at the same vertex. So for a circuit, if I start at B and then go to D, F, E, a circuit has to go back to the original starting vertex. So these two letters have to be the same. For a circuit, the beginning and the ending vertex have to be the same. A graph is connected if for any two of its vertices there is at least one path connecting them. Another way to talk about that is disconnected. So if they're not connected, they must be disconnected. So here are two examples of disconnected graphs. Notice I have this vertex D, which does not share an edge with any other vertex. And this graph right here, we have edges going in, but there's no edge connecting this part of the graph with this part of the graph. So we would say these are disconnected graphs. A disconnected graph is made of pieces that are connected by themselves, called components of the graph. We're not going to talk about disconnected graphs very much. Most of the ones we're going to talk about are connected. The homework is 4 through 48, every 4.